In this lesson, we're going to try to see and identify if a relationship is linear or exponential. So we have two problems here. Let's start with the steps that we need to figure out. Number one, what is my rate of change and what is my initial value? Those are the two things that we need to do. So let's start with problem number one. I know my x's are incrementing in 1. I found my initial value there when x equals 0, that's 40. Now I'm trying to figure out what the rate of change is in the y values. Both linear and exponential have different formulas. And I notice that my y values are changing and decreasing by 5. So they're subtracting by 5. That means automatically I have a linear relationship in my hands. So I'm going to use the y equals mx plus b. I have my initial value, which is my y-intercept, 40. And I can just start plugging that in and writing the equation. It's going to be y equals negative 5. Which means it's going to have a negative slope. The line's going to go downward. X plus 40. Every time I write an equation, I always want to plug in some values just to make sure that I have the right equation. So I'm going to do that now. I'm going to plug in 1 for x, and my y should be 35. And it works out. That means that I did the right equation. Let's look at the second problem here. My x's are incrementing by 1. That looks great. Again, I'm looking for what is the rate of change and what is my initial value. And I'm trying to figure out the rate of change, and I'm noticing that it's not quite adding. Since I identified my initial value when x equals 0 is 0.4, the hardest part sometimes is to find the rate of change. That's why I encourage everyone to use their stat functions in their calculators and plug in the whole table. It just makes it a lot easier once you figure out if it's either linear or exponential. I know that I was able to figure this out by multiplying by 1.5. In a fraction, this would be 3/2. So I have my rate of change there. And I want to plug in a couple of values in just to make sure that it works. But once you verify and find your rate of change, then you can just simply put that in your equation. Because I'm multiplying, it's going to be an exponential. And I'm going to use the equation y equals ab to the power of x. B is going to be my rate of change, and when you plug the numbers in, A is going to be your initial value. You end up with a function y equals 0.4 times 1.5 to the power of x. Again, I want to plug in some values just to make sure that my function works. If x is 1, y should be 0.6 if this equation is correct. And that looks good to me. So that function, it works. You can go ahead and graph it too, just to be sure that your initial value is in the right place. It looks like a 0.4 to me. All right, that's the easy part. The hardest part is always what happens when I have a word problem. So let's read this word problem. We have mold cells that are on a piece of bread. At the start of the experiment, there are 50 mold cells. Again, the process is the same. What is my rate of change? What is my initial value? And figuring out if it's linear or exponential so that you know what formula to use. I know my initial value right there when x is 0, y is 50. And I don't have the rest of the table, so it's a little bit hard to figure this out. But what I do know from reading is that the number of mold cells triple. That means we have a multiplication problem in our hands. My rate of change is going to be multiplying by times 3. Since I'm multiplying, I know I have to use an exponential model. So I want to use the equation y equals ab to the power of x. A is my beginning value. That's going to be 50. And b is going to be my multiplier, which is times 3. Once you have your equation, you can use that equation to fill out the rest of the values on this table if you want. So I can plug in for 1, check my answer, make sure that equation is working, and then use it to plug it in for the rest of the values. Question C is asking, on which observation will the mold exceed 100,000. So there are many different ways of finding that out, but with the equation, you can just simply plug in numbers and complete your table to find out. Let's look at another problem here. Julie gets prepaid cell phone. She has $40 balance on the phone. Each minute of talking cost is 15 cents. We have our initial value. Now we have to figure out what our rate of change is in order to write our equation. X is going to stand for the amount of minutes. And I can tell you right now, I am going to work this problem out as if Y, instead of being the remainder dollar value on the phone, Y is going to be the actual cost. So I kind of veered off the word problem a little bit just to illustrate a point here. I want my numbers to increase, and I notice that I'm going to be increasing by 15 cents as the minute goes up. And that is basically a rate of change of 15 cents. And I'm adding that to the value. And this is why I veered off from the word problem, because I wanted to illustrate a linear model. My initial value here is of $40. So when X is 0, when I have 0 minutes, I still have those $40 on the card. And as I continue, that is the amount of money that would build up. So it's a little bit different than what the word problem called for. I would have to be subtracting. So you would have to subtract 0.15. So it's not a whole lot different, but it's a little bit different. I worked this problem out a little bit different. What is f of 0? When x is 0, then we have y equals 40. And what is the value of f 100? Again, you can plug it in and figure out what that value would be. Because I worked out this problem a little bit differently, I'm not going to answer question E because it wouldn't work out for the way that I did this problem.